Welcome to physics for October the 20th. Before we jump into the homework, let's talk about a few important administrative details. So there will be a test today, or a quiz today. The due date for it is going to be Thursday at midnight. That's the due date for everything because the term ends on Thursday. So if you want to do any quiz retakes, you want to turn in any late homework, you want to turn any extra credit, anything at all that you want to turn in that you want to go on this term's grade, it needs to be received on Canvas by Thursday at midnight. Don't forget about the special extra credit problem. It applies even if you've maxed out your normal extra credit. You can still do the problem about driving on icy roads and hills. That will give you some additional extra credit and might possibly save your life someday because the knowledge that you get there. Most people who are new drivers don't realize how much you need to slow down, and it's way more than most people realize. Okay, let's see. So we are finishing chapter 5 today. We're talking about the last homework assignment today. So in theory, we could take a test today or maybe even on next time we meet next week. But I realize that a lot of this is new material, and some of the problems that I'm asking you to solve may be a little more challenging than problems that you've been asked to solve in the past. And so I realized that a little bit more review would be good. So what I've got planned for today is a lab activity. We're going to do a simple and yet interesting and worthwhile laboratory exercise, just using materials that you have lying around your home, and I think you'll learn a lot from it. It'll be really good. And so then you'll write up a report about that. That'll be your homework that will be due next time we meet, and then I'll give out the practice test next time, and then next week we'll take the actual test. All right, any questions about administrative stuff before we talk about last night's homework? All right, well then let's get into last night's homework. Okay, so you should now be seeing the answers to all of the problems that weren't in the back of the book. Some of these problems take a while to work through. So depending which ones you want to see, we might only have time to do one problem. I'm going to try to sneak in two, but we might only have time to do one. So let's take a vote. Please type into the chat box if you could only see one of last night's homework problems worked through. Which one would you want it to be? All right, I'm seeing a variety here. I'm seeing 102, 38, 101. Seeing 38 a lot, 97 a couple times. Let's get a couple more votes in here. Any of them doesn't help. Okay, 38 seems to be winning out a lot. 97, 101. All right, so 38, 97, and 101 are the ones that I'm seeing the most. Okay, let's try 38 because I don't think that'll take too long, and then hopefully we can get to either 97 or 101. All righty, let's share a screen whiteboard here. Okay, on problem number 38, we are working with the crate from example problem number 5. So if I flip back there, okay. So it looks like what we've got is a crate sitting on a ramp. This angle here, do they tell us what the angle is? Yeah, it's 30 degrees. And is there friction? They're not talking about friction. Okay, so if they don't talk about friction, we can safely assume there isn't any. They do tell us the weight of the box. Now, remember, weight and mass are not the same thing. If I ask you how much does a 1 kilogram mass weigh, the answer is not 1 kilogram. Okay, it weighs m times g. So a 1 kilogram mass weighs 9.8 newtons. So in this case, they're saying that the crate weighs 562 newtons. And so that is mg. We don't want to take that 562 and multiply it by g. They've already multiplied the m by g for us. All right, and so now in problem number 38, we want to find the acceleration, and after 4 seconds, how fast it's going to be going. All right. Well, by now you should have done enough problems that you should realize that we need to do a free body diagram. You know, my favorite problem solving strategy, draw a picture, and especially a free body diagram picture. That's really important. All right, so I like to do my forces in a different color. I highly recommend you do the same thing if you have that capability. So we've got mg going down. We've got the normal force going off like that. Now, if we had friction, friction would be opposing the motion. And so that's what it would look like. Now, in this case, we don't have friction, so we don't need it there. But, you know, if we did, that's what it would look like. And that's all we got. Those are the only forces. So one of them is clearly a funky force. And so you might be tempted to say, well, the funky one is the Fn because you like to put your coordinates like that. But remember the rule that I said is that if you have an object that is moving in some direction, it's vitally important that you align your coordinates with the direction that the object is moving. Super, super important. So we don't want to make our coordinate system be, you know, horizontal and vertical. What we need is we need to make our horizontal or our coordinate system be aligned with that direction because we know that's the direction it's going to move. And then the other one has to be perpendicular to that. So the funky force is not the normal force. The funky force is mg. All right, so we break that into its components. So we get a force like that and a force like that. And if this down here is 30 degrees, that means this up here is also 30 degrees. All right, so this side right here is going to be the hypotenuse times the cosine of the angle. And this one right here is going to be the hypotenuse times the sine of the angle. And now we don't need the mg vector anymore because he's funky and we don't like funkiness, at least not in our vectors. Maybe in our music we do, but not in our vectors. Okay, so we've replaced him with the components that do the same job that he does, but they do it in a nice, manageable way. All right, so now we're ready to figure out what the acceleration is, which means it's time to call in Newton's second law. So we're going to do sigma F equals ma. And now we got to pick, are we working in the x direction or the y direction? The x direction is this one, the way I'm defining it. The y direction is this one. So x direction is the direction that the acceleration is going to be in. So let me put an x there. And so let me just put a little x here to remind myself we only want the forces that are acting in the x direction. So when I make my little bracket here, and I say, what goes in the bracket? Well, any force that's acting in the x direction is what goes in the bracket, and I only see one. That's the only one that's acting in the x direction. So that's the one that goes up in there. So let's go ahead and put it in there. So I've got mg times the sine of theta equals mass times acceleration. All right. And now they told us what the weight of the box was. And so if we wanted to, we could divide by 9.8 and in order to find out what the mass of the box is. But this is one where they gave us a number that turns out we didn't need to know it, because if you look at the equations, you got an m on the right side and an m on the left side. If we divide by m, those things go away. So we didn't need to know what the mass of the box was. So get used to this, guys, that this is going to happen a lot. You know, I've done it to you on previous practice tests, and I'm probably going to do it to you again. And out in the real world, you're going to be flooded with information more than you need. So it's your job to figure out what is the stuff we need and what's the stuff we don't. All right, so it looks to me like the acceleration is just going to be g times the sine of theta. And we know what planet we're on, so that means we know g. And they tell us what theta is, so we can come up with an answer for theta. So I'm thinking we're good here. If we do it right, we should get the answer shown here. Doesn't want to share. There we go. We should get the answer shown here. 4.90 meters per second. Now, the second part of the question, they're asking how fast is it going to be going 1 second later? So that's just what I like to call a Dr. Seuss problem. Is where we use the equations of motion, which we get from the poster with the little Dr. Seuss picture on it. So if we want to know what is the final velocity, and we know what the acceleration is now, we didn't before, but now we do. Well, hopefully you guys remember there's an equation on there that says VF equals V naught plus AT. All right, V naught was 0. A we didn't know before, but we do now. T they gave to us. So yep, I'm thinking we can find that. And if we do it right, we should get 19.6. All right, so the other problems you guys wanted to see, it looked like it was kind of a tie between 97 and 101. Let's do 97 first, and then if we have time, we'll come in and do 101. All right, so 97, okay, that's an important one. Well, they're all important. I mean, every single one of these problems is like you might see on the test. They're all important. But let's open up a whiteboard and let's do number 97. All right. So we've got a sign and it's hanging like this, and it's being supported by 2 ropes. So one rope is coming up here like that, and this angle here is 30. Is it 30? Yep, it's 30 degrees. All right. And then the other rope goes off here horizontally to some other building. All right, and so we're going to call this rope A. We're going to call this rope B. That's a B. It may not look like it, but that's a B. That's terrible. Let's fix that. All right, and so our job is find the tension in the cables. Actually, I think all they ask for is cable B, but I'm suspecting we're probably going to have to find the tension in A as well. And it would be helpful to know the mass of the sign here. This time I don't think it's going to cancel out. Now, again, they don't tell us the mass, they tell us the weight. So they tell us the weight is 750 newtons. And the way they wrote it, it has 3 sig figs in it. So they wrote it as 7.50 times 10 to the 2. So that's 750, but it has 3 sig figs in it. All right, so remember, that is not the mass, that is mg. So they have already multiplied by g for us. All right, well, time for free body diagram. The pattern here, hopefully you guys see the pattern quite clear. All right, so let me switch to a different color. And so we got mg going down, which we know is 750. It's not 750 times g. It's already got the g built into it. So the weight is going down to 750. So if you got that wrong, good chance that you multiplied by g when you shouldn't have. That's what most people mess up on. All right, and then if we got a rope going off at an angle, that means the force is going to be going off at that same angle. That's always going to be the case with ropes. And so this rope is going to have some tension in it. So I'm going to call this TA. That's going to be the force pulling off at that angle. And then this other rope is going to be this way. So ropes always pull. If you've ever tried pushing a rope, you'll find it does not work. Ropes can only pull. All right. And so if this sign is sitting there motionless, which we certainly hope is the case, that must mean that all of the forces that are acting on it sum up to 0, both in the x direction and also in the y direction. Because if the object isn't moving, because you know, sigma F is really m times a, but if it's not moving, a is 0. So hopefully then, so if it's not moving, it will be 0. All right. So if we want to know tension B, well, let's try just working with the horizontal direction. If we get lucky, maybe we can do it with only one equation. So let's add up all of the forces that are acting in the horizontal direction. Okay, and we know that has to equal 0. And then we look at this and we say, wait a minute, that TA force there, it's neither horizontal or vertical. It's a combination of both. In other words, it's funky. So what do we do with funky vectors? Defuncify them. Now remember, when you go to another school, if you talk about defunctifying a vector, they're going to look at you really strange. So the official term is we want to break it up into its components. All right, so how are we going to do this? Well, let's say we've got a vertical vector and a horizontal vector. Let me take that TA there and let's move it to the other side, so they won't be in our way. Okay, so this angle up here is 30 degrees. I trust you guys realize that that angle down there is also 30 degrees. You remember from mathematics, alternate interior angles, all that fun stuff? Okay, so then when we break it up into its components, this side right here is going to be the hypotenuse times the cosine, so TA cosine theta. And this one here, up at the top here, is going to be TA times the sine of theta. So we don't need TA anymore because we replaced him with his components, which do the same job that he does, but they do it in a nice, manageable, non-funky way. All right, so now we can go ahead and we can put some stuff in here under sigma fx. So let's see, what forces do we have in the horizontal direction? I see this force and I see this force. So those are the ones that we want to pull up into here. Okay. All right. So now we need to have a plus direction. So most people like the plus direction to be to the right. So let's stick with that. So that means we're going to have TB minus TA times the sine of 30. We know what theta is. Let's go ahead and put that in there. So that has to equal 0. So we're looking for TB. Oh, rats, we don't know what TA is. We got two unknowns, only one equation. Where are we going to get the other equation from? Well, let's sum up all the forces in the vertical direction. That'll give us another equation. Okay, so let's say sigma F in the vertical direction must equal the mass times the acceleration in the vertical direction, which hopefully is 0 if the sign is not moving. Okay, so in the vertical direction, I see mg going down, and I see t cos theta going up, and I see somebody just made a comment, but my chat box is closed. Let me open that up. Okay, so somebody just asked me a private question. They said, why is TA sine theta negative? Okay, well, okay, thank you for asking that. That's an important question, right? The reason it's negative is because I defined my plus direction to be to the right. So when I look at this arrow here, it's pointing opposite of that. So that means it's pointing in the negative direction. Okay, that's an important question. Thank you for asking that. All right, so let's go back to here. So I've got mg going down. I've got TA cosine theta going up. And most people like the plus direction to be up, so let's go with that. Okay, so then that means that, okay, so we're going to have TA times the cosine of theta with the, and let me go ahead and put in the 30. I know what theta is. Let me put in the 30. Okay, that's in the plus direction, minus mg, which we know is 750. And that equals 0. So, hey, look at this, one equation, one unknown. So if they had asked us to know what TA is, we could have just worked with this equation alone. We wouldn't have had to worry about the one up above. Okay, but TA wasn't the one that they asked for. So, all right, so from this, we can now take that, we can take the 750 over to the other side here, divide by cos 30. So TA then is going to equal 750 divided by the cosine of 30. So once we know what that is, then we can stick it into here, and we can figure out what B is. I don't want to take the time to do that. I'm assuming you guys are good with simple arithmetic here. So I'm going to call it quits right there, if you're okay with that. If we do that correctly, we should find that TB is 433 newtons. Okay, so I just got another question privately saying, couldn't you point the arrow the other way? All right, so let's go back and let's look at it. Okay, all right, so the arrow has, the real force is not the components, okay? The real force is the red force that we see right here. That's the real force. All right, so the components have to add up to be the same as the real force. So the only way we can do that is if we have a vector that goes, oops, I hate it when I do that. I'm still in erase mode. I could swear I pushed the button to go out of erase mode, but it didn't. Okay, so here's our thing, and we've got the force TA going that way and TB going that way, TA going this way. Okay. All right. So if we want to replace this funky guy with some non-funky components, and we have to start where he starts, and we have to end where he ends. Those are the rules. You have to do it that way. So then the only way to do that is to go vertical and then left. We cannot go to the right. We have to go to the left. So the answer to the question that I was asked privately here was no, you can't do it any other way. All right. We could do 101. I think if we do 101 real quick, we could do it. But tell you what, I'm a little bit worried that we might run out of time. So let's do this. Let's hold off on 101 for right now. Let's talk about the lab that you need to do today and make sure that everybody fully understands that. And then at the end of the period, if we have some time left over, then let's spend some time working through 101. But I want to make sure that you guys get the lab activity, which is today. All right. So we are now finished with chapter 5 and also chapter 4, obviously. So we are ready to take the test, or at least I am, but I suspect that a few of you maybe aren't quite ready. And so I've got a lab activity that hopefully will help solidify some of the concepts that we've dealt with. I know from teaching over the years that friction is something that people need a little practice with getting used to, and also having forces that are acting on objects that are sitting on ramps. Those are sometimes a little tricky for people. So I've got a lab activity that's going to combine both of them and uses materials that you have sitting around at your home. Assuming you have a quarter sitting at your home, I think that's a safe bet. And assuming that you have a physics book sitting at your home, which you better. Okay, so here's what we do. I want to find out what is the coefficient of friction of a quarter that is sitting on a physics book. Okay. Now, you know that there are two types of coefficients of friction. There's static and there's kinetic. And if I wanted to, I really could ask you to find both. That would be a more interesting, fun lab. But I don't want to overwhelm you with stuff. I know that this is the end of the term and you've probably got math tests and other finals you need to study for. So I'll keep it easy. Let's just get the coefficient of static friction only, and I'll call that good. So how could I find the coefficient of friction, static friction, for an object sitting on some other object? Well, in theory, what I could do is I could push on this object with like 1 Newton and see if it moves. And if it doesn't, then I increase the force at 2 Newtons. And I just keep increasing the force until eventually the thing starts moving. And then we could go through some steps, which I'm not going to take the time to go through now. But in theory, if I just increase the force, and when I finally reach the point where it breaks free and starts moving, do a little bit of physics, and from that, I should be able to figure out what the coefficient of friction is from that. But I'm not going to do that because that would require that you guys have a tool that can measure how much force you're pushing with in newtons. And I doubt very much if any of you have one of those at home. Now, I have a bunch of them at school. If we were sitting at school, maybe we would do it that way. But we need something that you can do without using that force measuring tool. Well, it turns out there's a really simple and yet effective trick that can work. What we can do is we can take this quarter sitting on the book and we can tilt the book, and we see that the quarter doesn't slide. So obviously static friction is holding it in place. So we're going to tilt the book a little bit more. Still doesn't slide. Tilt it a little more. Still doesn't slide. But at some point here, it's going to. So I'm going to put my hand down here. So I'm going to keep raising this. There it goes. Okay, it just slid. So if I could measure the angle of the book, then I'm thinking that with that information. All I need to know is the angle of the book. I'm thinking that that would be enough to allow us to calculate what the coefficient of friction is. Now, some of you might be thinking, but don't you also need to know the mass of the quarter? Maybe, maybe not. I mean, if we're lucky, maybe it'll cancel out. All right, so what I'm going to do right now is I'm going to derive an equation that we can use to figure out what the coefficient of static friction is, if the only thing that we know is what angle do we have to tilt the book at before the quarter starts moving, okay? Now, your homework tonight is going to be to write up a lab report where you not only tell me what the coefficient of friction is, but more importantly, you need to tell me how you came up with that number. You need to tell me what equations you used, and you need to tell me where those equations come from, which hopefully you guys know is you need to know how to derive the equation. Deriving equations is something I think is incredibly important. That's what makes physics physics. If all I do is I just give you an equation, say use this equation, that's not physics. Okay, physics is figuring out where the equation came from. All right, so what I'm about to do, take careful notes, because when you write up your lab report, which is the homework that'll be due next time we meet, if you don't have this derivation in your lab report, you are not going to get a good grade. This is the most important part. All right, so let's open up a whiteboard and clear off what we got on it before. All right, so we're going to start with a free body diagram of the coin sitting on the ramp. So here is the ramp. Here is some angle, which we should be able to measure. If we have a protractor, we can easily measure it that way. Even if we don't have a protractor, we can measure it. Let's talk about that later. For right now, let's assume we have some way of measuring the angle. And here is some object sitting on the ramp. So this is going to be the coin in this case, but I'll draw it this way so it's a little easier to see. All right, now let's look at the forces that are acting on this object. So this free body diagram needs to be part of your lab report. All right, so what are the forces? Well, we're going to have gravity. So there's mg going down. We're going to have a normal force. So there's the normal force going like that. And we are going to have friction in this case because, as long as the angle is less than the critical angle, that coin doesn't slide. So that means friction is holding it in place. So we have the force of friction going that way, right? And so what we're doing is we're increasing the angle little by little until we reach the point where the thing breaks free. So we want to know if we're right at the critical angle, then we can say the force of friction is going to be mu static times the normal force. Now, some of you are going to say, wait a minute, Mr. Hendricks, you told us that the equation said that the force of friction was less than or equal to, right? So how is it that I can put an equal sign here? Well, if we are less than the critical angle, then we need to say less than or equal to. But if we are right at the critical angle, then we are at the fx max. So if we're at the maximum fx, or max force of friction is what I meant to say, we're at the maximum possible force of friction. So if we're at the maximum possible force of friction, then we can take that less than or equal, and we can write it as an equal as long as we understand that this is ff max, which is what we want. Okay, so if we want to get mu, then okay, I'm thinking we can just divide both sides by Fn. So we get mu static equals the force of friction max divided by the normal force. Okay, so you might say, well, but how could we measure what the force of friction max is, and how can we measure what the normal force is? Well, maybe we don't need to measure them. Let's come back and let's look at our free body diagram. And so hopefully you guys have done enough problems now that I can just go ahead and you recognize that the funky force is mg. So that's going to be the equivalent of these two guys here. So the one on the left here is going to be mg cosine theta, and the one on the right is going to be mg sine theta. Okay, so we don't need mg anymore. And so if we look at the, let's do the normal force first. So we can see that the normal force is equal to mg cos theta. So we can write that in there, just mg cos theta goes in there for that. And then the force of friction, okay? What is the force of friction going to be? Well, if the coin is not sliding down the hill, then that means that this force right here that's holding the coin in place must be equal to this force right here that's trying to drag it down the hill. As long as the coin is not moving, these two are equal. Now, if the coin is moving, they're not going to be equal. Okay, but if the coin is sitting there still, if we're right at but have not exceeded the critical angle, these two will be equal to each other. So in place of FF, we can just replace it with that. All right, so that means then that mu s is going to be the force of friction, which is going to be that. So that's going to be mg sine theta divided by the normal force, which is going to be mg cosine theta. And notice we got an m on top, m on the bottom. Notice we got a g on top, g on bottom. So what we've got then is the mu s then is equal to the sine of theta divided by the cosine of theta. And so if we measure theta, bingo, we know what mu s is. It turns out that it's just the sine of theta divided by the cosine of theta. Now, some of you in your math classes hopefully have encountered the fact that sine theta divided by cosine theta is the same thing as tangent theta. Let me just write that down just a little more nicely there. Okay, so that's equal to the tangent of theta. So this is probably the one that's going to be a little more easier to do, but I mean, not much. I mean, what's the difference? As long as you measure theta, you can calculate it either by doing sine over cos, or you can just take tangent. Try it out. You'll see that you get the same answer. Okay, so today's lab then turns out to be very easy, something that you could easily do using materials that you have at your home. I'm assuming you have a protractor at home. Now, if you don't have a protractor at home, don't despair. There's an easy solution to that, okay? But let's just do this again here. Okay, so what you're gonna do is you can take a quarter, put it on your physics book, take your protractor, put it up here. You're gonna lift the physics book and you're gonna measure your angle here. And you're gonna keep lifting and lifting and lifting until the coin slides. And when the coin slides, okay, whatever angle that corresponded to, bingo, that is the angle that you use. And so from that, you should be able to figure out what the coefficient of friction is. Okay, so you see this is pretty straightforward. Okay, so it's easy, right? Too easy, right? I don't want you guys to be bored. Okay, so how can we make this lab a little bit more interesting? Well, here's how I want to do that. I want everybody to measure the coefficient of friction for a quarter on your physics book. But I don't want you to stop there. I want you to find two other surfaces that you could put your quarter on. So in all cases, I want it to be a quarter, but it's going to be a quarter sitting on different things. So I want you to pick two things that you have lying around your house that you could put the quarter on and then tilt it at an angle and then measure the angle and see what the coefficient of friction is. So what I've done here is I've taken a piece of sandpaper and I've taped it onto my physics book. So if I put the coin on the sandpaper and then I tilt the physics book and I keep going up and up. So right now I'm at the same angle where the coin slid before. It's not sliding this time. Obviously the sandpaper has a lot more friction than the book cover by itself. So I just keep, there it goes. You see it start to slide there. Okay, there it goes. All right. So I'm going to get a different angle, which means I'm going to get a different coefficient of friction. All right. Now you don't have to use sandpaper. You can use whatever you've got lying around the house here. Some of you might possibly have a piece of wood, right? So what you could do is just put the coin on the wood, lift it up and measure that. So then you'll know what the coefficient of friction is for a coin on wood. Now this particular piece of wood is bare on one side and painted on the other. So I'm thinking there's going to be a different coefficient of friction on the painted side than there is going to be on the bare side. Okay. Maybe I'll get a piece of cardboard and find the coefficient of friction for the coin on the cardboard. Hey, here's a brick. Gee, I wonder what the coefficient of friction for a coin would be on a brick. Okay, so pick two other surfaces, but try to pick it so that one of them is a surface that you expect will be low friction, and the other one would be a surface that you expect would be high friction. Okay, so I just got a private message here, a couple of them. So one says, how exact would I like you to be with the angle measurement? Well, plus or minus 1 degree, please. All right, so if you're using a protractor, yeah, you can probably get that. But you know, there's actually a better way. Even if you have a protractor, but especially if you don't, you know, if you just take a ruler, you should be able to measure it, right? So let me open up a whiteboard, because it's actually easier to show this on a whiteboard than it is in reality. Okay, so let's suppose that we've got, this is the horizontal line, and this is our book, and our book is tilted like that, and here's the coin sitting on the book, and we want to measure this angle here, but doggone it, we don't have a protractor sitting around the house. Well, we probably are going to have a ruler. I mean, I'm trusting that you should have a ruler or some tape measure or something like that sitting around your house. Okay, so if you just measure, so when you get at the critical angle and the coin starts to slide, if you measure this distance right here, let's call this y, use a ruler to measure that, and to measure this distance right here, let's call it x, then bingo, you should be able to figure out what theta is, right? And in fact, maybe you don't even need to know what theta is, because what we really care about is tangent of theta, right? So if we just take y divided by x, bingo, there's the tangent of theta right there. So maybe we don't even need to know what theta is. But I would like to know what theta is. When you write up your report, even if you do it this way so you can figure out what the coefficient of friction is without actually calculating tangent, still, I would like you to tell me what angle that corresponds to. So please do that. All right, and so if you use this technique, I'm thinking you can get theta values that are even more accurate than they would be if you used a protractor. All right, and so I got another message from somebody who asked something that I think is very important, and I would have said this even if you hadn't reminded me. Multiple averaging is going to be very important, because what's going to happen here is when you do this experiment, so you take the coin, you put it on the physics book, you bring it up to an angle, and you see it starts to slide. There it goes. Okay. So if I measure that angle and then I repeat this and I do it a second time, it's entirely possible, and very likely, in fact, that the angle I get the second time is going to be slightly different than the angle that I got the first time. All right. So knowing that that's going to happen, the way we deal with those types of problems are we do 5 repeats for each surface. So for a coin on the physics book, I want you to do 5 repeats, and I want you to report all of the data. Don't just tell me what the averaged answer is. I want to see all 5 of the data points. Okay, this is an important part of doing a physics lab. You always want to show all your raw data. Okay, so for the coin on a book, 5 repeats. And then for the coin on some other surface of your choice, some hopefully low friction surface that you pick, I want to see 5 repeats. And then for the last one where you do the coin on some surface that you pick, which is hopefully a high friction surface, I want 5 repeats on that one as well. Okay. Yeah, not seeing any more questions.
I have a question.
Go ahead.
So you said to do 5 points. Does that mean you want us to like work out the math for, like 5 times for every every surface?
Okay, thank you for asking that. I've had several people wonder that over the years. Yeah, it turns out that if you take your input numbers and you average them, and then from that you calculate the answer, turns out you get the same result as if you had just calculated 5 different answers and then averaged those 5. You'll get the same result in the end, either way. Okay, and so now somebody just asked me a question. When I write the report, what kind of voice do I want it written in? So this person who just asked the question apparently has written lots of reports for another class. And sometimes the teachers are very specific. They want it in third person passive voice, or they say you can use first person voice. You guys know the difference there? First person voice is where you say, I did this, and then I did that, and then I did that. Whereas third person voice is the angle was measured. You know, instead of saying I measured the angle, you say the angle was measured and the value was found to be 37 degrees. Okay. Now, scientific reports do tend to be written in third person passive voice, but I don't want you to get hung up on that now. Later on, I might become more picky about that, but right now, use whatever voice you're most comfortable in. I don't want you to get so hung up on the voice that you forget about the physics. Okay, use any voice you want. But there are other things that I think are really important for you to know about the report and the way I want it written. And in fact, if you look on Aspire, if you look on Canvas, you will find that I have put a rubric on Canvas. So let me share that with you. So what you're seeing right now is the rubric that I have put on Canvas. And when I'm grading the report, this is what I'm going to be using as a guide. So I highly, highly, highly recommend that you have this rubric sitting by your side, looking at it while you're writing the report. Okay, so first thing that I'm going to look for, and this is going to be true for every report that we do for the rest of this year. And by the way, you will be doing more lab reports. First thing I'm going to look for is I want to see an opening paragraph, or at least a couple of opening sentences, but let's call it a paragraph. I'd like it to be an opening paragraph that is a brief introduction that clearly explains what the purpose of the lab is. In fact, tell you what, it might be hard for you to see that. Let me, switch to here. Okay, let me zoom in a bit. Okay, hopefully you can see that a little better now. All right, so I want a clear description of what was the reason we did this lab. Now, many of you are going to be tempted to say, well, the reason we did this lab was to find the coefficient of friction. Bzzz. Okay. Now, admittedly, you know, that is the stated purpose, but that wasn't the real purpose of the lab. The real purpose of the lab was for you to better understand how friction works on tilted surfaces. That's the real purpose. And so that's what I want to see in those paragraphs there. Okay. The real purpose was to give you guys a hands-on experience working with friction on tilted surfaces in order to help you better understand how they work together. That's the real purpose. Okay, now another thing that is true for every report that we're ever going to do is when I read the report, I ask myself, is this description thorough enough and clearly written enough that somebody who wasn't here today and therefore didn't hear my explanation, just by reading your report, could they understand what we did, why we did it, how we did it, and could they duplicate your results? That is pretty much the way that all scientific reports are measured by, is it clear enough and well enough written that somebody could duplicate the results based solely on what they see written there. Okay, next. I'm going to want to see a free body diagram showing the forces acting on the quarter before you broke them up into their components. Okay, so that means I want to see this right here, and I want to see mg going down. I want to see the normal, and by the way, label them. I want to see the normal force going up here, and I want to see the friction force holding it in place. And this is before you defunctified anything. Okay, I want to see one of those. And then I want to see a free body diagram after you defunctify it. So that means, so now we're going to see, and I want it to be a separate drawing. Don't do it on the same drawing. Okay, so we got the normal force, the friction force, and then we're going to have mg cos and mg sine. Okay, and go ahead and label them mg cosine, mg sine. And notice that the mg is missing now because we don't need it anymore. We've replaced it with the components that are equal to it. All right, so now next thing I'm going to look for in your report is I'm going to want to see I'm going to want to see how you took Newton's second law and inserted the forces from the free body diagram in there. So I want to see sigma F equals MA in the X direction. And then I want to see the little bracket. And then I want to see the forces that went in here. And I want to see that A equals 0. So that means all this equals 0. Okay. So I want to see all of that. And I want words that describe all of that. Okay, now I want a table showing the raw data. I mean, every year I always get students that they just give me the final answer and they don't show me the raw data. Showing me the raw data is really, really important because a lot of times people make silly mistakes along the way. It's like if you were taking a test, which you will be next week, if you just write down the final answer and you don't show me your work, if your final answer is wrong and you don't show me your work, I can't give you any partial credit, right? And some of you learned that the hard way on the last test. Some of you wrote in answers that were so close to the final answer that I think you probably just made a round off error, but I don't know for sure that's the case because you didn't show your work. So I couldn't give you any partial credit. But those of you that sent me copies of your work, I was able to give you partial credit. All right, so it's the same thing here. Show the raw data, show all the intermediate steps. Really important. Okay, next, I want at the end of the report, I want a summary statement that tells me, okay, so the mu value for the coin on the textbook was this, the mu value for the coin on the sandpaper was that, and the mu value for the coin on the cardboard was that, or whatever. So everybody does the coin on the textbook. Everyone does that because I want to compare the results. But the other two surfaces, they're surfaces of your choice. But don't just hide it in the body of the report. At the end of the report, I want a summary paragraph. And in that summary paragraph, tell me what it was, even if you told me previously in the report. Okay, and then one thing that's an Ames thing that you guys, I'm sure you've discovered by now, at Ames, we like people to reflect on what they did. And so I want to see a reflection section in your report, just a paragraph, or maybe just a couple sentences. And I want you to tell me what, as you did this problem, or as you did this lab, what are some of the difficulties that you encountered and what did you do to overcome them? What might you suggest so that next year when somebody does this lab, what suggestions could you give them so that they avoid some of the difficulties that you had? How could we do it better next time? All right. And then this last thing is important. This applies to all reports we're ever going to do. Even though this is not an English class, I'm gonna ding you points if you use bad English, if you use bad grammar, if you have poorly formed paragraphs, if you have run-on paragraphs. Man, I can't tell you how many times I've seen this, where people submit a report, and so I look at the thing, and one whole page is all one great big paragraph. Makes it really hard to read. Okay, so don't do that. Break them up into smaller paragraphs. Okay, so that rubric is on Canvas. So please, before you start writing your report, download the rubric, look at it, and have that rubric sitting by your side while you're writing the report. The report is due next time we meet. And that's about all I can think of to say about it. Do any of you have any questions about how to do the lab or how to do the report? Okay, so I just got a question saying, is it okay to handwrite the report? Please type it. I mean, you all have computers now. Otherwise, we wouldn't be talking to each other. So yes, type your reports, please. And now some of you are going to say, well, it should be single space or double space. Yeah, I don't really care much about that. If it was a rough draft that I was going to look at what you submitted and I was going to write little comments in between the lines, then double spacing it is nice because it gives me room to write my comments. But I am not planning to do that. So I would recommend go with single space.
I have a question.
Okay, go ahead.
So if you want us to type it up, how would you like us to show like all of our math work because it's kind of hard
Ah,
to
okay,
show
thank
it
you.
over.
Thank you. That's important. Yeah, so you're going to have to include a bunch of drawings, and you're going to have to include a bunch of equations. Now, most word processors can handle equations quite well, but a lot of students don't know how to do that, and it's not really worth your time to do it. And the drawings, you could do the drawings on the computer and import them, but again, it's not worth your time to do that. So here's what I recommend. When you type up the report, if you know that so you got a bunch of words right here, and then let's say right here is where you're going to put your drawing, just leave a bunch of blank space. And then when you print out the report, then you can go in by hand and you can draw in all of what you need by hand, all the equations and any free body diagrams, include those by hand. And then you could scan or photograph it and send me a photograph of your report there. Okay, so somebody else just asked me a question, but I think I just answered it. Any other questions? All right, so we now have about 25 minutes left in the class period. So we could use this time to get started working on the lab, or we could use this time to go back and do problem number 101. So let's take a vote. Would you guys rather use the remaining 25 minutes to get started working on your lab, or would you rather see problem 101 worked through? So please type it into the chat box. Okay, looks like, well, okay, most people are saying do the lab. At the very beginning, it was looking like most people were saying, let's do problem 101. But it looks like most of you are saying do the lab. So here, I know what we can do. Let's do this. Okay, if you want to get started working on the lab, you have my permission to go ahead and type bye into the chat box and log off. But those of you who would like to see problem 101 worked through, you stick around and let's do problem 101. Okay, so those of you that are leaving, goodbye. See you next time. Those of you that are sticking around, let's open up a white box, whiteboard, and let's get working on 101. Okay, so give me a sec to get to the right page. All right, problem number 101 is a really good problem. This is the kind of problem that I love to put on tests, wink, wink, nudge, nudge. So those of you that stuck around here, I think you're going to be rewarded on next week's test by watching this. Okay, so let me draw a picture. So what we've got is we got a ramp, and up at the corner here, we have a pulley. We have a mast hanging from the ramp, and the rope goes up around the pulley and comes onto another mast down here. And let's call this guy M1. Let's call this guy M2. This angle here is theta. And if I remember right, there is friction on the ramp here, right? Yes, there is friction on the ramp. Okay, so your job here is to find the acceleration of the blocks and also find the tension in the string. Okay, so like I say, this is one of my favorite problems. Wink, wink, nudge, nudge. All right, let's do a free body diagram. So we got M1G going down. We got the tension going up. And that's it for this guy. Now for the guy off on the left here, we got the tension pulling him that way. Now, is the tension on the left going to be equal to the tension on the right? That's the big question. And that all depends on this pulley. If that pulley is frictionless, and if that pulley has negligible mass, then the answer is yes, the tension on the left will be the same as the tension on the right. And in the high school physics class that you guys are taking right now, that will always be the case. Next year, when you take U of U physics, then you'll learn how to deal with a massive pulley. And because in that case, the tension on the right and the tension on the left will not be the same. But in this case, they will. All right, so we're not done with our free body diagram yet. We've got this guy over here, which is M2G. We got the normal force going up here, and there is friction, and the friction always opposes the motion. So if you look at the block here, in their picture, the block on the right is smaller than the one on the left. So that kind of makes you wonder which way the blocks are going to move. But then then they tell you that the hanging block is 16 and the other block is only 8. So the hanging block is definitely heavier than the other one. So there's no question the hanging block is going to move down. And so that means the block on the ramp is going to move up, and friction always opposes motion. So that means the friction force is going to point like that. All right. So now let's see if we can get some equations out of this. Let's do Newton's second law. So we know that sigma F equals ma. So which one do we want to work with? Well, let's look at this guy right here. Let's do him first. So under sigma F here, we're gonna have the tension and we're gonna have the mg going under there. But one of them is going to go in with the plus and one of them is going to go with the minus. So how do we know which is which? Well, we need to pick a plus direction. If M1 is heavier than M2, then we can be pretty certain it's going to move down. So I recommend let's take the plus direction and define it to be the direction that we know they're going to move. And remember, when we choose the plus direction for the guy on the right, that also determines the plus direction for the guy on the left. So if the plus direction for the guy on the right is down, then the plus direction for the guy on the left has to be up. Otherwise, we're not being consistent. All right, so when we take these forces here and we put them under the sigma F there, then that means the tension force goes in with a minus sign, and the mg force goes in with a plus sign. And then, oh my goodness, I left out the A up there. How did I leave out the A? Hey, you guys, if you point out mistakes like that, I'll wear the wig. But if you leave them for me to discover them on my own, then sorry, no wig for that. Okay, now which M is this? Well, this is M1. So this is equal to M1 times A. All right, so here's an equation. And so M is a value we know, G is a value we know. Here's that same M. Oh, there's the A that we're looking for, but rats, there's also a T in there. So we got two unknowns and only one equation. What to do? Well, we need another equation. Where are we going to get the other equation? Let's look at the guys over here on the left. So let's do the same sigma F equals ma, but this time it's for the guys on the left. All right, so sigma F equals ma, but this time it's m2a, and these are the forces that are acting on mass 2. All right, so, okay, let's see, what have we got? Now, we only want the forces that are aligned in the same direction that the acceleration is. So we only want the ones, so if we draw our coordinate system like this, so this is our x, and that's x, and this is y. We only want the ones in the x direction. So it looks like we got some funkiness we need to take care of. Okay, that's easy to do. So we take mg, we break them up into its components. So we got mg cosine theta, we got mg sine theta, and so we don't need mg anymore. All right, so what have we got? Well, looks to me like we've got tension going in the plus direction. We got the force of friction going in the minus direction. And we got mg sine theta going in the minus direction. And remember, that's m2g sine theta. So that's equal to ma. All right. Okay, but we don't have a number for the force of friction. So looks like we're going to have to do a little bit more work here. So what is the defining equation for force of friction? It's mu times the normal force. What is the normal force equal to? Well, if we were on flat ground, it would be equal to mg, but we're on tilted ground. So if you look at the normal force here and you compare it, you see that it's equal to mg cos theta. So that means the friction force is equal to mu times mg cosine theta. That's the friction force. All right, so let me clear a little space here. Let me get rid of this just so we have room. I'm going to need more room. Okay, so what we're going to have then is we're going to have the tension minus the force of friction, which is mu times mg, that's m2, g cosine theta minus m2g sine theta equals m2a. All right, so there we are. There's one equation. Here's the other equation. From this point on, it's no longer a physics problem. Now it's just a math problem, and you're good at math, right? Okay, so could you guys take it from here and solve it from here? Or would you like me to finish this all the way? All right. So I'm seeing in the chat box, you're saying that, okay, once you got to this point, you can take it from here. Because from this point on, it's just math, and heck, even Mr. Jensen can do math, right? And by the way, you can tell him I said that. In fact, please do. All right, well, I'm thinking we're done. Are there any more questions from you guys? Oh, wait a minute, I just got, somebody just told me yes, and I don't know what yes means. Does yes mean yes, you want to see the rest of the problem, or does yes mean yes, you're good and you can go? Not seeing a response. Okay, could I go back to the notes real quick? Okay, yep, can do that. Okay, so tell you what, we've got time. Let's finish it out. Okay, now I need some space here, so I hate to get rid of the picture there, but we need space. So I'm gonna go ahead and get rid of the picture. And let's go ahead and let's just finish this baby up. We've come this far and we've got time, so let's do it. Okay, so the idea with, so we could either use substitution or the elimination method. In this case, the elimination method is going to be a little bit easier, but you really could do it either way, I promise you. All right, so with the elimination method, the idea is we take everything on the left side of this equation and add it to everything that's on the left side of this equation. And then we do the same thing on the right side. We take everything on the right side of this equation and we add it to everything on the right side of that equation. And when we do that, we're going to find out that the t's are going to cancel out. So what we're going to have on the left side here is we're going to have m1g, which is that, minus that, which is mu times m2g cosine theta, okay, minus m2g sine theta. Okay, so that's on the left side. So that then has to equal what we have on the right side, which is m1a plus m2a. And so we want to solve for a, so let's factor out an a. So we got a times m1 plus m2. Okay, so this then equals that, okay? I just don't have enough room to write it the way that I would prefer. So if we then divide both sides by m1 plus m2, what we're going to get is all of the stuff up in the upper left here divided by m1 plus m2. So this then equals a. Bingo. So from this point on, it's just plug and chug. So I'm not going to take the time to do that because we know m, we know what planet we're on, so we know g, we know mu, bingo, yep, we know all those. Okay, so we can get a number for a. Once we got a number for a, we can take that number for a and we can plug it back into this equation right here, and then we can figure out what t is. And so I don't see the point in going through all that. We good? Okay, not seeing anything, not hearing anything. Okay, I am seeing the app. You're good. Okay, well, all right, so get working on the lab. Good luck on that. And I'll see you guys next time. Okay, goodbye.